Hello and welcome to day 7 of Unit 5. Today we're going to be talking about mean value or average value and looking at some applications of the theorem. So the vocabulary for today, obviously average value, and how do we define that? We define average value to be, the average value of f is 1 over b minus a, that's a b minus a, the integral from a to b of f of x dx. Now obviously, since we're taking the integral of f, it must be the case that f is continuous on the closed interval a to b. Okay. Okay. That has to be true in order for the average value to exist. But if that's true, then the average value does exist. And now how do we make sense of this? Well, we go back and think of mean value. Now, I don't want you to get the two confused. Average value is a value. Mean value is a theorem. The mean value theorem said that if f is continuous, again, on some closed interval a to b, then there has to be some value c such that f of c times b minus a is equal to the integral from a to b of f of x dx. And the picture that we drew for that looked like this. Some function from a to b, the area underneath, which is the integral, somewhere between a and b, there is a point, C, where the value at C, that height, times the width of the interval, which gives me the area of this rectangle, must be equal to the area under the curve. That was the mean value theorem. The mean value theorem guarantees the existence of C. Guarantees the existence that there is a value between A and B such that this is true. Well, this can be rewritten to fit that. If I just divide both sides by b minus a, I get that f of c is 1 over b minus a times the integral from a to b of f of x dx. So, what's the connection? Mean value theorem guarantees the existence of a c. The average value is the f of c in mean value. Okay, the average value is the f of c in the mean value theorem. So let's go ahead and get rolling and look at a few examples of some applications of this theorem. All right, so first up, right off the bat, we have a direct example. And by direct example, I mean it's just find the average value. Okay, there's not really any thinking involved here. The average value is defined as 1 over b minus a, integral from a to b of f of x dx. So we're given all that information. All we have to do is plug it in. Okay, so the average value of f, a, b, e, 1 over b minus a, which is 3, the integral from -1 to 2 of 1 plus x squared dx. All right. So the integral of 1 plus x squared is plus x cubed over 3 from -1 to 2. So we get 1/3 2 plus 8 over 3 minus -1 minus 1 over 3. Alright, so I'm going to go ahead and multiply through here because, let's see, we get a 2/3 plus 8/9 plus 1/3 plus 1/9. Okay, so I have 8/9 and a 9th is 1, and that's 1, so 2. So the answer is 2. So average value is 2. Answer. Okay. Okay, so given this question, find the value of c in the interval from -1 to 2 such that this is true. Here's that. That's what I'm looking for. The question by itself can be rather complicated, but if we recognize that this is just mean value theorem, and remember how we connected mean value theorem with average value, then really this is just which we've already done. This is 2. So all I'm looking to do is find the values of c such that f is 2. In other words, when is this true? When we subtract 1, we find that c is equal to plus or minus 1. Answer. Now, graphically, what does that look like? There's my curve, my interval, a little bit off, but forgive me. And I believe this was the last question from day 5, where we said, okay, we have the area under the curve here. And we said, or we wanted to know, what values of x do I get the average value, right? And so it just so happens, now my graph's a little bit off here, but it should be 1 and -1. Okay. Graphically, that's what's happening there. Now, the area of this rectangle represents the average value. No. The y value here represents the average value. That's this. Okay. Or this, the average value. Okay. The mean value theorem says that these two c values existed so that the area of this green rectangle was equal to the area under the curve on the same interval. Okay. Okay, so I know exactly what you're asking yourself. You're asking yourself, great, Mr. Southern, I've got this definition for average value, but how does that help me? How am I going to ever use that? Well, here is an application that you might not use in your everyday life, but will allow you to see the possible application of average value. Now let's say that I'm an engineer, a structural engineer, and I have this metal rod, okay, it's metal rod, and this metal rod is, say, connected to a furnace, okay. Right, and there's fire in this furnace. Okay, so obviously this rod's going to get hot. Okay. And we say that the temperature of this rod, we're going to measure the temperature in this rod from here. Okay. So the temperature in this rod, as we get closer to the furnace, is represented by 4x. Actually, let's change this. We're going to change the problem. We're going to say the temperature is represented by negative 4x. So we want the temperature to, and I just want this to, it makes more sense for the temperature to be, okay, so decreasing from here to here. So as x gets larger, as we get further away from the furnace, the rod gets colder. Okay. And I don't know, maybe this has a its initial temperature of, let's say, 300 degrees. Okay. So it starts at 300, and as we go along, it gets cooler and cooler and cooler and cooler. Okay. So red hot here. But then it starts to sort of cool off. Okay. And we want to know what the average temperature is of the rod. Here, the rod is 300 degrees, but however here, it's some other value. It's some distance away. Now this rod, what are we going to say? This rod is how long? How long is this rod? This rod will be 5 meters. 5 meters long. Okay. So out here, the rod is 280 degrees. However, here the rod is 300 degrees. Okay. As we move along, the rod gets cooler. We want to know, what's the average value? What's the average value of this rod? Well, we want to find the average value of T. Okay. And we want to find the average value on the interval from 0 to 5. That's the whole rod. Okay. Now T of x is negative 4x plus 300. Okay. The average value requires me to do this. Okay. All right. So we get 1/5. See, the integral here is going to be negative 2x squared plus 300x from 0 to 5, which is, see, 5 squared is 25 times negative 2 is negative 50, plus 5 times 300 is 1,500. Oops. Right? See, 1,500 minus, let's go ahead and divide everything by 5. Divide everything by 5, I get negative 10 plus 300, so the average temperature is 390. Now, I like this problem because it's easy to see that this truly is the average temperature. Excuse me, 290. Because if the temperature is 300 here and the temperature is 280 here, and then the average should be somewhere right in the middle. And that's only because the temperature is decreasing at a constant rate. It's decreasing at a rate, the temperature's rate of change, as we get further from the furnace, the rate of change is -4. But had this been like -4x squared, then the rate at which this cools is not constant. The rate at which this cools is -8x. So it's getting cooler faster the further away I get from the furnace, which is actually probably a better representation of what would really happen in a scenario such as this. But for simplicity's sake, I like this example. So make the adjustments on your notes. I like the way this worked out better than the one that was in your notes. So that's an application of average value when I might use it. And that's it for today. Thanks for watching.